Assalamu alaikum warahmatullahi wabarakatuh. This is the next experiment. That means the design of the counter. Actually, you can say we are using making a 4-bit counter with the 4 flip-flops and which can count from 0 to 15. With 4 bits, we can count from 0 to 15. So in this counter, there are 4 flip-flop, JK flip-flop. All the inputs to the J and K for all the flip-flops, it is equal to 1. And note that this flip-flop that we have used, it is positive edge triggered flip-flop, not negative edge triggered. So that is the reason. Actually, if I give my input to the next flip-flop clock as Q complement, I have to actually give. Then if I give Q complement to the next stage, then it will function as an up counter. If I give Q as the input to the clock of the next flip-flop in each stage, then it will be acting as a down counter. So to do this, serve this purpose, actually I have created a control input from here, and this output, for example, Q has been taken and feed it to the XOR gate, and you can see here 1 is coming. So you know 1 XOR any variable will be the complement of that variable. For example, Q is coming here, and Q XOR 1 will give you Q complement here. So if I put this control input as 1, then I can say Q complement will be reaching the clock, so that it will be counting up. Similarly, the same control signal I am using for all the flip-flop. The same arrangement has been given to all the flip-flop. So I need actually 3 XOR gate, and you know how to place it. And if you want to place the XOR gate, you can place by using this method also. XOR, you can use it with the 2 input XOR gate. That is also possible. So the JK flip-flop you can easily available. You can see here, this is JK flip-flop. You can place the component JK flip-flop by typing JK. And you know this is the DCD hex. It is a display, and you can just write it is a decade DCD display. From here you can select it. Okay. And for the display, this is the least significant bit and this is the most significant bit, and the output actually we have to take it from the Q, and this is Q. You can see that this is the least significant bit. We have to be very careful. The first one is the least significant bit, and this one will be the most significant bit, because it is a frequency dividing circuit. You know that the counter is a frequency dividing circuit, so you will be getting half of the frequency here, then half of half, that means 1/4, then again it will be 1/8, like that. Okay, so that is why this will be the most significant bit and this is the least significant bit, and this is the circuit diagram. Let us run it. So you can see I have already given another input from here, which is a control input to reset actually all the flip-flops, so that it will start with the value 0, but everything is active high, so I have to give high, then only it will reset. So when I give high, you see the flip-flops actually reset, and the values are now 0. So let me put it as 0 for the normal operation. Now after the normal operation, you see it is counting, and the count will start from 0 and it will end at F. Okay, that means 15. So this is the arrangement for the asynchronous counter. Okay, so which can do both up and down counting. Now you see, if I give the value of this as 0, it will count down. Let us see now. This is 0. See now, it is counting down. F, E, D, C, B, A, 9, 8, like this. Okay, so this is counting down. So this is the arrangement. So next we will see how we can make a mode n counter actually. So we will make a mode n counter. That means this counter can count from 0 to 9. Okay, and the 10th value actually will be when the 10th value, when the value 10 is arrived, actually what will happen, it will reset all the flip-flop. That means you know that 10 means in binary it is 1010. So what I will do is that this 1010, so this is the least significant bit. So the least significant bit will become 0 when it becomes 10. So you know that I will take the complement of it. Similarly, the second least significant bit, you can say that that output is taken from here, but that is directly used from here. From here it is directly used. And the third one, you know, it is 1 0 1 0. Third one will be also 0, so I had to complement it. Then everything I will be putting into a 4 input AND gate. You can place it like this. So if you just search it, and then you can say 4 input AND gate, you can select AND 4. Okay, so then it will be calculated. So when it will become 1 0 1 0, the output of this AND gate will be 1, and that is directly applied to reset all the flip-flop, so that the flip-flop will be resetted. All the flip-flop will be resetted, and the values will be going to 0. So after 9, the 10th value, it will be going to 0, because it will reset the flip-flop. So this is what the arrangement, and you see that the Q complement of this flip-flop is connected to the clock of the next flip-flop. So the Q complement of the first stage is connected to the clock of the second stage, not the Q. Why? Because we want to count up, and we are using a positive edge triggered JK flip-flop, not negative edge. If it is negative edge, you have to connect the Q to the clock of the next stage. So let me run the simulation. See, 1 2 3 4. Then you see that after 9 it will be 0. So this is how to make a asynchronous 4-bit counter which can count from 0 to 9. Thank you.